Okay, hello everyone. So we move on to recursive algorithms. Just some things about the reading. So this is the main part. Excuse me, that I want you to read. There's more examples of recursive algorithms in these sections. All of them are on the syllabus, but just so you know, this is the priority. These sections have extra examples, which you should read because it's beautiful stuff. It's the recursive sorting algorithm and recursive search algorithm, assuming that the data structure is sorted. Okay, so they just are another examples of very beautiful recursive algorithms. And here is some background reading, and just another word of note. The book, starting from section, oh, this is a typo, it's 8.12. I don't know how. Anyway, I meant section 8.12 here. I'll fix this. It starts talking about asymptotic notation for running time. So starting here, but also when it analyzes when it talks about the running time of either the merge sort or the binary search and other examples here, it uses this asymptotic notation. Basically, you can read, it's pronounced theta of whatever time function. It's a function of usually input size. So say you are sorting a list of n elements, this function f will be, in that case, n log n. It gives you a running time of the algorithm, but for binary search it will be log n. So these are two different examples of functions f. And these sections will contain expressions like theta of some function of n, and you can read them as basically that it's approximately whatever this function inside is the running time. If you want to know exactly what this theta notation stands for, first of all, everybody in computer science should learn this asymptotic notation, okay? So if you don't know what this stands for, by all means, go and read it. But I will not require this in this class. So, you don't need this for this class. If you read here and you read this theta, you can just, if you really don't want to read what this is truly about, then just think of this as approximately whatever the function, okay? And I will not require anything more from you in this class. On the other hand, this is an absolutely fundamental concept, so you should know it. Well, here is the pointer. Okay. Okay. So yeah, the other section somebody asks, they're missing sections here. Yes, they're on the syllabus. They just don't talk about recursive algorithms. And today we're doing recursive algorithms. On Thursday we're doing the sections that are basically missing here. Yeah, like 8.8, 8.9. Yeah, I guess those two. All right. So somebody says that they don't understand asymptotic notation. Okay, good. So here is your pointer for how to understand it. Okay, and of course, okay, it's not a trivial concept. You have to think a little bit what this stands for. But you really don't have to for this class. Okay, this is enough for this class. Okay. But it's like you can, I don't know, if you have some questions about it, post them on Piazza, use office hours or discussions to learn more about it. Okay, we will be talking about algorithms. So how do you write algorithms? Okay, like this is not an algorithm class, it's not a coding class. We'll just we'll use something called pseudocode, which is kind of language neutral. a way of stating what an algorithm does. So it's not C++, it's not Java, it's not any other programming language really, but every code that we give you, if you know any particular language, you can map it into it. And so the syntax is informal. It's just a means to convey the steps. Like, and we are not gonna hold you responsible for any formal syntax. Like, as long as you communicate what an algorithm does in some way that we can understand, that's fine. The less language specific stuff, you know, if you give us some sort of C macro, like, I'm not a coder, so I won't be able to understand it. So make it simple, make it you know, somehow general. So you can say if predicate then expression else some other expression. You can use the loop construct, like for I equal 1 to n. In fact, we will not use this because, or rarely, because we'll talk about recursive algorithms. Or assignment, you can use this for an assignment, you can use equality for an assignment. This is fine, as long as we can tell that this is an assignment rather than test. Yeah. Okay, let's see some examples. Okay, but first, what is a recursive algorithm? So recursive algorithm is an algorithm that has two discernible parts. One is called a base case. So for certain class of inputs, intuitively, for inputs which are in some sense small, smaller than some threshold, the algorithm is going to evaluate the outputs, the output on those inputs somehow directly. But for larger inputs that are not falling into this small class, the algorithm will compute the output by calling itself on some smaller inputs, and then using the results of these calls to combine them and derive the output from some combination of outputs of the recursive calls. Okay, in fact, I gave you an example of a recursive algorithm. It was a merge sort. When I and this is formally described in sections. So it was one slide or so on my lecture last week, but you have this beautifully described in one of these sections, right? Okay. So these calls to themselves are called recursive calls. Now, this is kind of a mouthful, but notice that recursive, we have seen an example like this, of a recursion like this, in the context of defining sequences. They were called recurrence relations. And these were sequences where at some small indexes, typically 0, 1, 2, right? The elements of the sequence at those indices were defined in some say directly. Like, for example, in Fibonacci sequence, they were just declared. 0 index was declared to be 1. The first index element was also declared to be 1. You can think of them as part of this base case definition, right? I mean, they were part of the base case definition of the Fibonacci sequence. Now, for indexes that were larger, not in the smaller class, the Fibonacci sequence was defined recursively in terms of Fibonacci sequence elements at smaller indices. You can think of this as a recursive call to the Fibonacci algorithm on inputs where you want to define what's a Fibonacci sequence at point n. Well, we're going to make a recursive call to a Fibonacci algorithm at point n-1. Then we're going to make a Fibonacci sequence call to a Fibonacci sequence algorithm at input n-2. And whatever they return we just take an add, and that's what the Fibonacci sequence at point n is going to output. This is actually exactly an example already that you know. It's an example of a recursive algorithm. Every recurrence relation is a recursive algorithm that defines this, that computes that sequence, right? The recurrence relations were recursive algorithms. They were not written as algorithms. They didn't have on input, output, on, they didn't have if-then structure, but you can render them in this way, okay? And they are one and the same thing. Okay, but now basically what we're doing is that we're generalizing this. You already have seen recursive algorithms because recurrence relations are examples of recursive algorithms. These were recursive algorithms that define sequences. But you can use recursion to define other things, not necessarily a sequence, but some other objects. For example, you can use recursion to sort lists or to search in lists. And these are not exactly like a sequence, right? So it's a generalization. Let's see. Here is an algorithm, for computing exponentiation in a recursive way. So an algorithm, I'm going to call it a power algorithm. It will have two inputs, A, the base of exponentiation, and N, the exponent. And so the A is like any real number. N is assumed to be an integer and it's assumed to be non-negative. Okay, so starting from 0 and up. And what we want this algorithm to output is simply A to the power of N. So here is a recursive code that does compute it. Algorithm power on inputs A and N performs the following fork. If the exponent N is equal to 0, then the algorithm just returns value 1. It doesn't do any further computation, it just returns 1 as an output. Now that's good because indeed A to the 0 is 1 for any A. Okay, but if the exponent is not 1, it's not 0, we assume that it's a non-negative integer, so therefore it's a positive integer, so it's 1 or higher. The power algorithm is going to do this. First, it's going to perform a recursive call to itself with changed inputs. The base will actually be the same, but the exponent will be decremented. So it will be 1 less, okay? So in other words, if you say call this power at A, 5, okay, then it will generate here a call to A to power at argument A, 4. And if you look at what this does, it will not be here because the exponent will be 4. So it will generate another recursive call to the same algorithm, but with the same base A and now exponent 3. And so on and so forth until it hits the base case. Okay, but let's see what it does on the return. So let's say that it returns some integer, some value. This code is going to say, okay, let's call that, whatever this returns, let's call it P. And what I will return now is whatever this was multiplied by A. Okay. So you can see, okay, why does this work? Okay, because you see, whenever there is this recursive call, the exponent decremented by 1. So a call to A, 5 is going to generate call to A, 4. That is going to generate A, 3. That's going to generate A, 2, A, 1. Finally, A, 0. All right, that will return 1. Now, what happens on the way back? So this thing will return 1 when N was 1, then N minus 1 was 0. So this will return 1. So P is going to be make 1. Okay, for N1. So what will power A, 1 return? It will return 1 times A. So in other words, it will return A. That's good because power of A with exponent 1 is indeed A itself. When that will return, so what will be A power of A, 2? Well, this we already convinced ourselves will return A, because this is power A comma 1, and I just explained that we're going to return 1. So here P is going to be A, and it will return A times A, in other words, A squared. And you can trace the same thing to sort of convince yourself that indeed it will always, on the way back, this will be multiplied by as many A's as N, as N was, right? As basically N times this multiplication will happen. Okay, we can argue this. What has happened? What kind of reasoning is this? It's an inductive reasoning. The base case was correct, and the nth instance of the problem is tied to the n minus first in a correct way, namely by this relation. And so we can argue that this is correct everywhere for every input n by induction. Okay, so here is a little code. Okay, here's the claim. For any integer n, this algorithm returns correct exponentiation, and it's like regardless of the base. Indeed, the base is constant throughout, right? Like it's always, if it starts on any a, it's going to call with the same base a, so you can treat it as a constant. And the proof is by induction. So what's the predicate? The predicate as a function of n is that this algorithm returns the correct value when it's called on input n. And a doesn't matter, it's a constant. So the predicate says it's true for every a. That's the predicate we're going to prove by induction on n. So first point, right? We're proving it for every n at least 0. Okay, so the base case is clearly n equals 0. What does this predicate say for n equals 0? It says that when I call it with a comma 0, I will get a to the 0, which is 1. And that will be true for every a. Well, that is indeed true about this algorithm. When it's called with n equals 0, it triggers this line, it returns 1, end of proof. End of the proof for the base case. Okay, so now inductive step. What are you proving? You're proving that for any k at least 0 and up, if the predicate holds on k, then it holds on k plus 1. That's the inductive proof, right? What's the predicate at k? The predicate is at k, that power algorithm, when invoked with n equal k, returns a to the k. So that's what you can assume. That's your inductive hypothesis. And under that hypothesis, what you want to prove is this. And what is that? That is that the power algorithm, a is a constant, on exponent n k plus 1, will return a to the k plus 1. Okay, so let's see whether this indeed follows from that. And it does, okay? Why? If k is at least 0, then let's look what does this algorithm do on these inputs. Well, the input is k plus 1, so in other words, n is equal to k plus 1. If k is greater or equal to 0, then k plus 1 is greater or equal to 1, and therefore this line is not going to be triggered. So what the algorithm will do, it will trigger this and then return that. Okay, so in other words, it will return a times p for p equal to power a of n minus 1. But n is k plus 1, so therefore n minus 1 is k. So the algorithm will return a times power ak. Now, by inductive hypothesis, you know what this returns. Or rather, you don't know, but you can assume that you do. Okay? That's the inductive hypothesis. You assume, you give it to yourself. Assume that for k, it was correct. Okay? In other words, this thing will return a to the k, and there is your proof, because if p is a to the k by the inductive hypothesis, then a times that is a times a to the k, and of course, a to the k plus 1, and you're done. Yes, because that's what you were proving. You can see that basically, well, let me just show it on a piece of paper. This is the same as a this is nothing but a recurrence relation in disguise, right? So a recursive algorithm for power went like this. Power an was if n0 return 1, else set p to be power a n minus 1 and return what? Return a times p. Okay, so you have this recursive algorithm, right? And now what's really the difference? Recursive, what would we call it? Recurrence. Okay, sorry for misspelling. Recurrence relation. That defines really the same thing. Could be defined like this: a0 is 1, right? And an is defined as a times a n minus 1 for all n greater or equal to 1. Okay, this and this are the same thing, right? How are they the same thing? Just let an be defined as power an, right? So what you had here was this, and this thing was this, right? So this recursive algorithm, what does it do? I mean, and of course, this line is the same as this line, right? So there's two parts here: base and recursive. Base and recursive. The base one defines what's the power at point n equals 0. Well, the base here defines what's the sequence at index n equals 0. Okay, what's this? Yeah. And the recursive part defines what's the output at point n, and how does it do it? As we're using this relation to an output at point n minus 1. Well, that's exactly what the recurrence relation did. It defined the nth element of the sequence with some code in relation to the n minus first element of the sequence. Well, this is this code, right? Here. Okay, so nothing new is really happening. It's just a different guise, right? And not surprisingly, if we used, we used recursion, induction to prove something like this. That for every n, the nth element of the sequence has this closed form. And here we used induction to prove that for every n, power an returns an. Yes, I mean the parallels are obvious, and they are exactly because of this correspondence between these two things, right? So the inductive proof to prove this for this recurrence relation, indeed, it's identical to the inductive proof we just did, which proves this about this piece of code, right? Because these are the same things, just kind of like in a thin disguise. Okay, so go back If you have questions, shoot them. Okay. 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 Let's do something slightly different, okay, but very, very similar, really. So there's the same piece of code, right? The recursive code, which I was just arguing is nothing but the old recurrence relation in disguise. And let's argue that we have already argued that it creates a correct output. Yeah, but let's just show that it performs exactly n multiplications. So, in this code, there is some cost to setting some space for this code to execute, subtracting, assigning. But these costs are small compared to this is the cost. Like when you're having integer operations, this is the most expensive part. So you can sort of pretty well approximate the cost of this in terms of like, well, how many multiplications did it do? Okay, and it does exactly n. And this is your new predicate that you want to prove for all n. Okay, it's not about correctness anymore, it's about the running time. And there's the two basic questions about every algorithm. Is it correct? Good. How long did it run? How much space did it need? And so forth, right? But this is the most basic question that you would ask. And I had this in a slide a few lectures back, but in this 8.13 chapter, you sort of look at like merge sort and really see like why does it run in approximately n log n time, right? But here is a simple example of that. The proof is going to be by induction on n. Okay, it is not sort of obvious that that's how you should prove it, right? But when you look at this, this should click that you should prove such stuff. You should in here the induction is sort of clear because the first thing is n0, then the nth is clearly defined in terms of n minus first. So this is some process on integers, right, which is natural to prove by induction. Sometimes this might not be so apparent. There might be some other variables going, and you will have to identify, what is the parameter that you should make an induction on. Okay, perhaps it's not any, perhaps it's a length of a bit string that the algorithm computes on. Perhaps it's the total length of all inputs that the algorithm computes on. You will see other examples. Okay. Okay. So here by induction on n, for n is equal 0, the algorithm performs no computation. Well, that's good. Indeed, it performs no multiplication. Now in the inductive part, right, assuming that power with k performs k multiplications, we will argue that power with k plus 1 performs one more. And the proof is very clear from this code, right? So if indeed power ak uses k multiplication, then clearly power k plus 1, going to again omit that line, run this one, and n minus, if n is k plus 1, then n minus 1 is k. So therefore, by inductive hypothesis, this took k moles, and here is one more, right, in this line. So therefore, the total is clearly k plus 1, you're done. Right? But these proofs are sort of really very immediate, right? Because they mimic, recursive algorithms are perfect for proving stuff using induction, right? Because they have induction is a recursive reasoning. If something works for k, then I'm going to argue that it works for k plus 1, and therefore recursively, because it works for k plus 1, then it works for k plus 2, and recursively works for k plus 3, etc. This is exactly how recursive algorithms work, right? Like something can be done at n minus 1, and therefore it can be done at n, and so forth, right? So they are just the exact match for one another. Okay, for the next example, let's do like a quick refresh. You should remember these two laws for exponentiation, right? B to the x times b to the y is the same as b to x plus y. And when you have b to the x and then you take it to y, that's the same as taking b to the x times y. So let's do a quick test. What is this? You have options here. C, yes, right? So it's 2 to the 3 times k plus 1. You use this rule. So it's 3k plus 3 in the exponent, correct? Right. Okay, let's continue. So 4 times 2 to the k. Okay, which of these it's gonna be? So 4 is what? It's 2 times 2 to the second power. Yes, so it's this one, because this is 2 to the second. So it's 2 to the second times 2 to the k, it's 2 to the 2 plus k. So it's okay. So let's do a faster algorithm for exponentiation, which will perform fewer modes and like dramatically fewer modes. So think of exponentiation where n is really huge. Okay, and we'll use exactly that in cryptography algorithm examples a week from now, right? So if n is really large, then doing it linearly in n is going to be a bottleneck. Okay, here is a modification of this algorithm, which goes from linear to logarithmic in terms of number of modes. Okay. Here is the algorithm. So it has the same inputs, the same outputs we request of it. The base case is the same. If the exponent is 0, it just returns 1. But in the recursive case, it does differently. It divides rather than decrementing the exponent. That's what the previous algorithm did, right? It just, in this case, it just decremented the exponent by 1 and ran recursively on that decremented 1 and multiplied the result by a. Okay, here you do a dramatic shift down, dividing the exponent by 2. And because n might be odd or even, you have to divide over the integers. So that's called integer division. So this is basically the floor of n divided by 2 floor. That's your d. Okay, it's a divided exponent. Now you run recursive algorithm power on this half smaller exponent d, and when whatever this algorithm recursive call to the same algorithm returns that value, now you return up in 2 cases. If n was even, then you square the result, and if n is odd, then you square the result and multiply it by 1 more a. Okay, let's argue this is correct. Okay, so here is the code again, same code, but just called FP instead of FastPower to save space. And that's the ticket I wanna argue, and now I'll argue it by strong induction. Why strong induction? Because a recursive call, if I call an algorithm on input n, this generates a recursive call that is not n minus 1. It is some smaller exponent, but not smaller just by 1. So inductive hypothesis, if I try to use standard induction, then the inductive hypothesis that I could use was that the algorithm performs well on an integer that is just one smaller than the one I try to argue that the algorithm performs correctly on. That's not a useful form for this algorithm, because the outputs at the point n are not, it doesn't matter what this FP algorithm output on input n-1. What does matter is that what the FP algorithm outputs on inputs that are definitely smaller than n, but not necessarily just by 1. Okay, so base case is same, right? N equals 0, and when I go for 0, it just returns 1, which is correct. That's good. That's the base case. Now, in the inductive step, we'll show now you will use strong induction. So we'll show that if we assume, for any k, if we assume that the algorithm returns correct outputs on any input, as long as this input is smaller than or equal to k. Okay, so it's correct on all integers up to k. Then we'll argue under that stronger, more powerful assumption that the algorithm will actually output the correct value at point k plus 1 as well, right? Because the algorithm depends on whether acts differently on arguments that were even and arguments that were odd. So we're going to handle these two cases separately, okay? Just because of the nature of this algorithm, it just performs differently on even n and on odd n. So therefore, we'll argue separately for these two cases. So let's do case k plus 1 is even. In other words, I'm looking at I'm trying to argue that FP for n equal k plus 1, well, it will not hit the base case, right? Because k is greater than 0, so k plus 1 is greater than 1. But it will do this. And because kn is even, so it will return this. It will return p square. So let's argue that, let's see if p square is correct under the inductive hypothesis, which should tell us that this part is correct. Okay, so let's, okay, so if k plus 1 is even, so it's 2m for some integer m. So this d included here, which is what? It is n divided by 2 over integers. N is k plus 1. So, but if k plus 1 is even, then you just, this is simply k plus 1 divided by 2. So it's k plus 1 divided by 2, so it's that m. Now, this value is smaller than k plus 1. It's in this range, right? It's smaller than k plus 1, so it's no bigger than k. And it's also not negative, so it's no smaller than 0. It's somewhere in here. So that's where you couldn't use standard induction, which because standard induction only allows you to assume something holding for one smaller point. But strong induction says, okay, it doesn't matter. If it's anywhere in here, you can assume by strong inductive hypothesis that algorithm was correct on it, right? That's the form of the strong induction. For every element input that was smaller than the one you need, you can assume that the algorithm output correctly. Right? That's what's in here. So by correctly means that the output here was a to the n. You can ask, like, why don't I use g here? Okay, I could simplify this. I just didn't want to force my values to be related to the some variables that are used in the code, okay? But d and m are indeed the same thing. So fp of am will return a to the m. That's the inductive hypothesis. So p is going to be a to the m. And so because n k plus 1 is even, right? That was this case. So the algorithm will return p square. p square, where p is this, and by inductive hypothesis, this thing is a to the m is computed correctly. So therefore, squaring this gives you a to the 2m, and 2m is k plus 1. So that case is correct. Okay. I mean, it's as simple as this. If n is twice something, in this case twice d, and this code outputted correctly, so it output a to the d, then when you're squaring it, you're squaring a to the d. And what is that? That's a to the 2d. And n was 2d. So it's a to the n. Okay, that's it. Okay. Let's look at the okay, so if you don't interrupt me, I assume that you don't have questions, you know, but you just have to pipe in if something here doesn't look right, or you have any other question. Okay, so let's look at the odd case. I did it separately because the algorithm is going to compute slightly differently. Okay, so if it's odd, so it is 2m plus 1 for some n, right? And again, let's look at what this code does. Well, we'll skip that line, it will go here, and b, which is n divided 2, where now n is 2m plus 1. So when you do the div 2, you're gonna get m back. Okay, because now this is an odd, but we're going to basically lose this part because of the integer division. So it's m. So p is a to the m by inductive hypothesis. P is going to be computed correctly, a to the m. And let's see that this is the correct way. Given a to the m, this is how you're gonna compute a to the k plus 1. Why? Because this code, a times p square, is this, which is a2 by inductive assumption, a to the m square. So this is a to the 2m plus 1 more. And this was your n, right? Because it was your k plus 1. Okay. So it is correct again. It's not difficult. What you can stumble upon is the changes of variables. You know, which one is n? Okay, like the input here is n. No, as in all proof by induction, you know, sometimes the choice of variables works very beautiful. Yes, but then you have to do one less, or as in this case, half less, and the variable is not going to fit so nicely. Or, you know, for an odd case or for an even case, it might work differently. So there's always some friction at these interfaces. So, you know, just have patience with them and don't try to like rush through it. So you might, you know, overlook what was n, okay, in your head. Write it down and separate this sort of clearly. Okay, okay, that's the only source of difficulty here. And my lesson is just, you know, have a little patience and maybe slow down slightly, not to make this not to avoid mistakes. Okay, now what this I don't have on the slide the running time algorithm argument for this. So And I want to draw some parallel to some sequence that we have already looked at earlier. So FastPower on AN had this structure. If n was 0, return 1. Otherwise, compute G, which is n div 2. Okay, so just integer division. Set P to be FastPower AD. Okay, and then if n even, then return p square, and if n odd, return a times p square. Okay, so that was that, and it computes powers correctly. Okay, what about the running time? Okay, so first, like, let's look at this as a sequence. Okay, so now the recurrence relation. So here is the recursive algorithm, and here is the corresponding recurrence relation. So let's okay, so the first element of the relation is this, yes, and then there is the recursive part. Okay, so the nth element will be how about a fork here based on whether n is even or odd, and it will be a half of n. So in other words, this element squared if n even, and if n is odd, then I will take element that was computed like this. The index of the element was computed. Okay, the integer division when n is odd is really the same as just get rid of the 1 and now divide, because after you get rid of 1, then this becomes even, right? So you divide, and that's the element, the index of the element of the sequence, pointed to by index by d, as understood as an index into the sequence. And what did we do with this element? We squared it, and we multiplied it by some constant a. Okay, and that's what we did with n is odd. So here is a recurrence relation. It has two clauses, like it defines a nth element as a function of some previous element, differently for the case of n is even, and differently in the case of n is odd, but that's okay. It's still a recurrence relation. It's still some function of previous elements. It's just the function takes as additional input, if you will, whether or not n was odd or even, right? So we have remember this example where we had a sequence defined like this. A0 was 1, and an was defined as a and n div 2. Well, actually, I could recast this in this language. Okay, so using this language, this would be like this: a0 is 1, and an is a n div 2 squared if n even, or a times a n div 2 square if n odd. Yeah, so that's the same. This is n div 2 for n even, and this is n div 2 for n odd. Okay. In this example, this actually an was about log n. that was the conclusion. This type of sequence grows logarithmically. The same reasoning will show you that this code performs logarithmic number of multiplications. Okay, so claim fp of n performs okay, and now yes, because I have to use this log_n modes. So because I don't want to formally define this, focus. Then I would just I would just do this. So to avoid this, I will argue a modified claim, which is that fp n performs makes 2 log_n modes for all n which are powers of 2. Okay, so I will make this claim on a very small subset of inputs, namely only powers of 2. This algorithm works for arbitrary n, yes, but you can maybe convince yourself that if this claim is true, so if here is powers of n, this is 0, which is 2 to the 0, then there is 2, then there is 4, then there is 8, 16, yes, and so forth. Now, if for n equal 1, it performs 1 mode, 2 modes. If for 2, it performs 4. Here it performs 6. Here it performs 8. Here it performs 10, right? Etc. Then maybe you can see that if n falls in between these, then it will perform in between this many. And then you will understand what that means. It's just, it's an approximation sign. Okay. How do I get this? It's because it's 2 log_n, right? So log here. Oh, no, actually, here it will perform 0. Here it will perform 2, 4, 6, 8, and so forth, right? So let me argue this informally. For n equals 0, it's true, right? Because it's it doesn't perform any okay, n is 0 is not even it's not even a power of 2. The first power of 2 is 1. So end of 2 is a 0, so it will perform no multiplications in this call. It will just return a 1, and then it will go here because n is odd, right? So it will square that 1, that's 1 mult, and then it will multiply it by 8. That's a second mult. Did I say? Okay, I guess I have to go back to this. Okay. Sorry. Okay, let's see for the next power. Okay, so at for n, which is a power of 2, we definitely, it's an even case. So okay, sorry. So it will perform just 1 more. So it will do as many moles as the previous power. I'm arguing. Okay. So fp on a 2 to the I let's say, does what? D is if n is 2 to the I, then D, which is n div 2, is 2 to the I minus 1. And since n is even, you return, okay, now you compute P, which is FP A to this D, which is this, and you return P square because n is even. So number of moles performed by FP on A to the I equals 1 plus, because here you perform a single mold, number of moles performed by FP on A to the I minus 1. So in terms of n, number of moles done by FP of AN is 1 plus number of moles done by FP on A n over 2. So therefore, let's define AI stands for number of moles done, AN done by FP on AN, and we have the following recurrence relation: AN is equal to 1 plus A n over 2. In other words, it's 1 plus A n div 2. Oh, you know what? This was a stupid example. It was this in our example, right? If I defined like before, that would be a pretty boring sequence. It will always be 1. Yes. So our example was definitely not this. It was that. We incremented by 1, but not previous element, but an element pointed by an index which is half the given index. Okay. Sorry. Okay, now it's hopefully makes sense. So this is the code and this is the claim. So it is the same recurrence relation, okay, that was here. It is the same recurrence relation. Therefore, AN is about log n. And this is just a recursive part of the relation, right? So I also have to define at the beginning what happened, right? So what was A0? It's 0. Yes, because for A0, you know, how many moles does this algorithm do? For input 0, it doesn't do any moles. It just goes to the base case. Okay. Okay. Maybe that was confusing for some. Maybe some of you followed this. Anyway, if you have questions, let me know. Because this thing, you know, the fact that this code is just as correct as the simple power, okay, that doesn't show that's good, but it doesn't show like, so what's so special about this? Well, what's special is that its cost measured in terms of number of multiplications is characterized by this recurrence relation. Okay. And this recurrence relation, as we already argued a week or so ago, grows like this. Okay. And you can argue this very cleanly for n, which are powers of 2. Then in that case, it's exact equal to the logarithm. For everything that falls in between, it's not hard to see that the number of moles must also fall in between. And so therefore, we have this approximation. Or if you want to be formally, you use this theta notation. Okay? For our purposes, either one is fine. And you know, as I don't know if you know, but like, you know, the difference between n and log n for large n is dramatic, right? Okay, so let's go back to other examples. If there's no questions on this. Okay. So, okay, here we have maybe a different way to look. Okay, you have some goal. Okay, you want to compute the following expression by a recursive algorithm. Let's fit a recursive algorithm so that it computes this. The recursive algorithm has two parts. So there is a base case for some initial n. Okay, in our case, this will be n equals 0. Okay, because we want to compute it for non-negative integers. So in the base case where n equals 0, we just have to compute this value directly. Okay, so if n equals 0, then the code, okay, what is it? It's 3 to the, if n is 0, then this is 1. So this is 3 to the 1, which is 3. So the algorithm should just return a to the 3. Yeah, this should be the base, the base case line. And now assume that the recursive algorithm you just showed a different example where the recursive call was not to n-1, but to some other much smaller, namely n div 2 indexes. But let's say that this structure is going to be just call the recursive call is just going to be to the call n one smaller index. Then what should you return given such value? In other words, okay, how do you write this? So you should write thinking recursively. If a to the 3 times p, okay. So if this recursive call returns correct, so what does it mean? That this is a to the 3 to the this exponent. So it's a to the 3 to the n. If you knew that, how would you compute this value? Okay, so then just do it on a piece of paper and see how would you compute this value as a function of a to the 3 to the n, to the a to the 3 to the n. Okay, so here is one, but actually I think this. Okay, so if p, this recursive call returns correct, which I argued is a to the nth power of 3, then if I cube this result, then what happens with the exponents is that 3 to the n is now multiplied by 3. In other words, I get this. And now I can see that this is 3 to the n plus first. So it's that, which is what it should be. Okay. So how can you reconstruct these things? Okay, like, well, assume you have just try an error, right? Like try the recursive call to be 1 less and see whether this function can be described this value can be described recursively as some function of the previous value. What is happening? It is like, it is the, okay, before you were given a recursive relation and you were asked, okay, what's the closed form of the relation? Now you're going back. This is the closed form. Let's write a recurrence relation for the same, to define the same sequence, but recursively, right? So here it is on a piece of paper. Okay, it's too bad that this thing gets defocused every time. Okay, so we want to compute the function like this, a to the 3 to the n plus 1. Okay, so this is the function of, it also has an a as a constant, but really the important part is n. Okay, and the code for this was that if n is 0, return a to the 3rd, and otherwise compute p, which is fa of n minus 1, whatever this algorithm did, and return p cube. Okay, so claim, okay, so this we want to, this is, this is the goal. Yes, but this is the code. Okay, so this is what what we claim is that above code for FA achieves that FA of n is a to the 3 n plus 1 for every a and n. Okay, and a proof by induction on n, and the proof is done for every a. Okay, so base is that if n is 0, then fa of n returns a3, and that's indeed a to the 3 to the 0 plus 1. So we're done. Inductive step is that assume FAK outputs a to the 3k plus 1 for any k, for some k. Prove that FAK plus 1 returns a 3k plus 2. Okay. So this is up to the variable name. Maybe it's better to call this k minus 1, this k plus 1, but okay, I wrote this, we're stuck with that. Okay, so let's prove this. So what does fa of k plus 1 return for some k that is greater or equal to 0, right? Because we proved it for 0, we want to do the induction for any point after. Okay, so k is greater or equal to 0, so k plus 1 is greater or equal to 1, so this does not kick in, this kicks in. Okay, so then p is fa of k plus 1 minus 1, right? So here n was k plus 1, right? So this is fa of k, and by the inductive hypothesis, this was correct. Okay, so if p is correct, then p to the cube is a to the 3k plus 1 to the cube, which is a to the 3k plus 1 times 3, right? Because this is sequential exponentiations corresponds to multiplying exponents, and now multiplying exponents with the same values with the same base means adding exponents. So this hidden exponent is 1, and if you add it, you're gonna get 3 to the k plus 2, which is what we want, right? Okay. Now let's see that the same exact proof, would work. Let's render this as a recurrence relation. So what is the recurrence relation? As recurrence relation, and here is as recursive algorithm, right? So this is the recursive algorithm, this is the recurrence relation. What's the recurrence relation? Okay, let's say that somebody gives you the following relation. The first element in the sequence is a to the cube, and then the next element of the sequence is defined as the previous one cubed, and that's for all n greater than 1. Okay, because n is defined as the root n minus first, right? So we have to set it like that. So this guy is, the first guy is 0 here, which is base case. Okay, as you can see, this is exactly the same thing, right? The base case is this, and this recursive step is right here. So this code is again nothing but this recurrence relation in disguise. And if somebody says, what would this recurrence relation be an answer to? If somebody said, okay, let's say that I have a sequence like this, which is defined by in a closed form way using this formula, a to the 3 n plus 1. Please give me a recurrence relation that defines the same sequence. Here is the recurrence relation. The first guy is a to the cube. The nth guy is the previous guy cubed. Yeah. So filling in, creating a recursive algorithm to compute some, complex, you can say, arithmetic expression is exactly the same mental exercise that just, a week or so ago we would call, here's a closed formula for some function, defines a sequence, define that sequence using a recurrence relation. It's the same thing. Okay. Okay. So let's do we have some other examples here? Let me check. I think I have one more. Aha, yes. So my last example of a recursive algorithm is is an algorithm that writes out power sets. Okay, so the input is some set, and I want to write out the power set of that set. Okay. So in other words, write out all subsets of an input set A. Here is the recursive algorithm. The recursion is going to be on the size of set A. So what's the minimally sized set? Okay, it's an empty set. So if my input is an empty set, then I will compute the power set of that directly. It's simple to do so. The power set of an empty set is a set whose only element is an empty set. Indeed, the only subset of an empty set is an empty set itself, so therefore that's the only element of a power set. Okay, what's the recursive case? That's a if A is non-empty. Okay, in that case, if it's non-empty, then we can pick some element in it. okay, because it contains at least one element. So the code will say, this is the code I give. It picks some element in this input set. It's a little funny piece of code because it's non-deterministic. I don't tell you which element you should pick. Somebody says it will be like, how about the first element? Well, sets are unordered, so there is no notion of a first. Okay, but you can say, okay, you know what? They are unordered, but they're different elements, right? So I can ternally order them, because if everything on Earth, okay, can be described as a bit string. So it's a big thesis, right? I mean, as first, if you're a computer person, then yes. If you're a theologian, that maybe not necessarily. Yes, but hey, you know, if you're a quantum physicist, then perhaps not necessarily. So anyway, if pick an element in the set, and if all these elements are described as bit strings, you can just you can make it the bit string with the smallest in alpha numerical order, but you can do any choice here. Now let B be a set A reduced by removing that chosen element. Okay. So now whatever the size of the input set was, set B, you can say definitely what the size of it is. It's one less than the size of A. So that may be a good moment for some recursion. Indeed, we're going to run a power set algorithm on that reduced set, which is reduced just by one element. So its cardinality is just one less than the cardinality of the input set. We will assume that the power set worked. Let's see with this power set on this reduced set B. Now, how do we go from the power set on this reduced set to the power set of the target set A? Well, we'll go like this. First of all, notice that because B is a subset of A, all elements in the power set of B are already elements of the power set of A. What this contains is every subset of B. And every subset of B is clearly a subset of A. In fact, half the subsets of A are included here. Because if you divide subsets of A into two classes. First class, all those subsets that do not contain the little a. Well, all those subsets are in fact already here, because subsets of capital A that do not include the little a are subsets of B. And therefore they're in here. So what are the missing subsets? It's the second part of the partition. It's those subsets that do contain the little a. But look at those subsets more closely, in a sense. They contain a little a, that's for sure. And what about the rest? Well, the rest is the subset of B. Yes, because the whole thing is a subset of A. It does contain the little a. The rest must be a subset of this reduced set. So that's how I'm going to recreate these missing subsets here. For every element in this power set, which is, in other words, S is some subset of B, I'm going to extend that subset by adding the little a into it. And this will form a new subset, namely the subset of B with the little a added, and I'll add it to my set of subsets. And that's it. Oh, sorry, this is supposed to be the capital C. Yeah, and now just return that. This is a recursive code. It's on the homework. And on the homework, you should, what it asks you is to, well, I kind of work through it, right, by justifying the code. My intuition for why this code works was formally can be mapped to an inductive reasoning that argues that this code is correct. Again, this is a typo. This should be this set C. Okay. That this recursive code works. The inductive argument, the variable of induction is the cardinality of the input. Okay, because indeed the base case corresponds to cardinality 0. And in the recursive call, if you're calling it on a set of cardinality n, then the recursive call here will be for some set of cardinality n-1, right? Because this set has one less element than the initial set. So it's prime for induction, right? And okay, so when I end here, this is just proof of correctness of this is by induction, and it's part of the homework exercise. Of course, the book has more examples, and there are more examples in additional exercises. So try to do them to be, to sort of practice this activity of, mapping a recursive algorithm to a sequence, arguing using induction, and connecting all of this stuff. Okay. So I will end here, and I'll stop recording. And if you have questions, please ask them.